Welcome everybody here at GESIS Mannheim to our GESIS research talk. Today we have a special guest, and I think that the attendance is showing that he is already quite renowned in his area of interest. So today I welcome David Kaplan as our guest speaker, and you may have wondered, if you haven't heard of this name before, what you would actually find out about him on the internet. If you Google his name, you might come across several people who are named that way, but he is not the philosopher from LA. He is not one of the two particle physicists, one actually coming also from Wisconsin, and he's not the film producer. So in case you have turned up for one of these people, I'm sorry to disappoint you.
I will go pick up his Nobel Prize, though. That's one. I'll pick it up.
Actually, David Kaplan is a Patricia Busk Professor of Quantitative Methods in the Department of Educational Psychology at the University of Wisconsin-Madison. He has several affiliate appointments at the University of Wisconsin's Department of Population Health Sciences and the Center for Demography and Ecology. He's also an honorary research fellow in the Department of Education at the University of Oxford. He is an elected member of the National Academy of Education and a recipient of the Humboldt Research Award. So he has been to Germany before. He's a fellow of the well-known German Institute for International Educational Research, the DIPF in Frankfurt. And I may say that his research is particularly focused on methodological issues, specifically Bayesian issues. When I tried to count the numbers of his publications, I gave up quickly, not only because of the confusions with the name and several other fellows named in the same way, but there's just too many to mention here. I would like to mention, though, that he has published in some of the methodological flagship journals of our discipline, for instance, structural equation modeling and multivariate behavioral research. I think he already has, but also will have a long-lasting impact on our field by means of the two books that he published on structural equation modeling and Bayesian statistics in the social sciences. And this is particularly why we got you here today. Regarding grants and sponsorships that he received, it's the same situation. I cannot quote them all. I would just like to mention that he has recently received, with a couple of other investigators, a $3.5 million grant on longitudinal study of vocabulary growth and phonological development by the National Institute of Deafness and Other Communicative Disorders. So he is also known because he's actively involved in the OECD PISA program, where he has been member of the technical advisory group and the questionnaire expert group, which he actually chaired in 2015. And you're still a member on that group. Right. Before I lose too many words on his impressive CV, I would rather like to hand over the word to David. Today we have not only a roughly 30-minute research talk as an introduction to Bayesian statistics, but David is also so kind to give us a little tutorial on how to actually implement these statistical approaches in our own research agendas. And so we will have like a little break in between for people to come and leave, have a short break, and then we will continue with the tutorial afterwards. So please give a warm welcome to David Kaplan.
Thanks so much for the kind introduction. It's great to be in Mannheim again. I've been here a couple of times before, but to Germany many times for the last 15, almost 20 years. I've been coming here almost once a year to the DIP. So we have a lot to do in 30 minutes. I have to tell you everything there is to know about Bayesian inference, which is going to be challenging. It's going to be, if nothing else, mostly a vocabulary review or lesson. I have no idea what your backgrounds are in terms of this, so for some it might be very simple, for some it might be brand new, and everything in between. So it's always good to start with a picture. This is Bayes, although I just read the other day that they're not, in fact, entirely sure that this is him. And the way that they figured this out is they figured out that if he was a reverend during this particular time, then he wouldn't have this particular collar. So they think it might be somebody else from a different branch of the Anglican Church, apparently. So that's Bayes anyway. We'll just assume that that's him. And this dapper gentleman is Pierre-Simon Laplace, who should actually be credited with Bayesian inference. It should probably be rightfully referred to as Laplacian inference, because he proved the theorem that Bayes has been named after. So I start these workshops and quick lectures with a quote. This is another gentleman, Jerome Cornfield, who says that it is clear that it's not possible to think about learning from experience and acting on it without coming to terms with Bayes' theorem. And that's what Bayesian statistics is about. It's learning from data in a very direct and, I would argue, very intuitive way. So I don't know what the kind of quantitative training that one has here in Germany for the social sciences, but mostly Bayesian statistics tends to be overlooked. You might have an introduction to some of these ideas in the part of your statistics course in probability, or if you had a full course in probability, you would likely have been introduced to Bayes' theorem. But some of the reasons why it tends to be overlooked, or used to be at least, is that it was simply not feasible to conduct statistical analyses with Bayesian tools. They didn't exist. So you couldn't do it. And that there wasn't any SPSS or Stata or SAS little pull-down menu that would allow you to do Bayesian statistics. But perhaps another reason, a little more deeply rooted, is that it represents a very powerful alternative to frequentist statistics, and it's, as a function of that, it's controversial. They're now popular, though. Bayesian methods are now popular because, at least since the late, maybe the mid-'80s, we've had popular statistical software tools, mainly through the package called WinBugs, that's made its way into roughly common practice. And so you're now seeing many more papers using Bayesian tools. So what I want to do, rather quickly, is talk about the major differences between Bayesian and frequentist paradigms, Bayes' theorem briefly, priors, Bayesian computation. We'll leave some of that also for this workshop afterwards. Bayesian hypothesis testing, Bayesian model building, and then some conclusions. So the idea that if you want to think about these as paradigm differences, the first big difference is one's conception of probability. And it turns out there's actually very many conceptions of probability. But the two we're going to worry about is probability represented by long-run frequency and probability represented by subjective belief. And they're different. In the frequentist case, probability is represented by long-run frequency. We have this idea that we have equally probable and independent events. It's more of a metaphor, if you will, or a construct. And the physical representation of that is the coin toss. So when you were taking a course in statistics and you were sitting around tossing coins, or at least pretending like you were tossing coins, that's what this was about. It was about the notion that we have equally probable and stochastically independent events, and in fact, actually an infinite number of them. And this idea underlies Fisherian statistics, basically conventional methods of statistics that we often use, including the Neyman and Pearson hypothesis testing schools. Mm-hmm. So again, the entire structure of statistics as we typically practice it is grounded in this idea that an experiment can be conducted an infinite number of times under exactly the same conditions, stochastically independent, an infinite number of events. Your conclusions regarding null and alternative hypotheses presuppose the idea that you can conduct this thing an infinite number of times. And this thing doesn't have to be an experiment as you might typically understand the word. Any observational study makes that presumption, whether you like it or not. That's what's going on underneath it. Confidence intervals assume that there's some fixed parameter, and it's the confidence intervals that vary under repeated experiments. But the other view of probability, counter to this, is the notion that probability represents subjective belief. And here, if you want a physical model similar to the idea of the coin toss, the best model for subjective belief is betting. So you can consider a situation on who's going to bet, what your bet would be on who's going to win the World Cup, or in my case, the just completed World Series. So here, your notions of probability are not going to be based on sort of conducting a soccer season exactly the same way under exactly the same conditions, necessarily. But rather, how much knowledge you have about the team you're betting on, and perhaps more importantly or relatedly, how much you're actually willing to bet on that, the actual money involved. Right? So I can say that a certain team, I think a certain team is going to win, and that's great, but it doesn't really help me until you tell me how much money you're going to put on that bet. That tells me what your prior belief is. Right? Those two together at any rate. So subjective probability allows you to address questions such as, what is the probability that my team will win the World Cup? Now, it could be that you have frequency information, frequency data that supplies information. So you might have a team that's played for years and years and years and never won. Right? And I know soccer works a little bit differently in terms of being relegated to another level. Baseball doesn't work that way. But that relative frequency certainly supplies information, but it's not the same as probability, and it can be quite different. Because my subjective probability, my information might be different from your information about that team, but the frequency data is exactly the same. You and I see the same number of wins and losses over a long period of time, but I might have more knowledge about the team than you do, in which case my subjective bet will be different even under the same relative frequency information. And it's this notion of subjective probability that underlies Bayes. So we can take some observable events just to introduce the idea in case you have seen it before, or not. Let's take a look at two events, the joint probability of observing lung cancer and smoking. So take an epidemiological example, very simple. And we know from basic statistics that we can write the joint probability of these two events as the conditional probability of cancer given smoking times the probability of smoking. But because these two, this joint probability is symmetric with this joint probability, I can also write it that way. Two different conditional probabilities multiplied by two different base rates. So this represents the proportion of individuals that smoke in the population, regardless if they have cancer or not. This is the proportion of individuals in the population that have lung cancer, whether they smoke or not. So now, because those joint and conditional probabilities are symmetric to each other, I can write the former equation this way. And then, as long as the base rate of smoking in the population is not 0, I can divide by this, and now I have this conditional probability expressed as this conditional probability multiplied by the ratio of these two base rates. But because of that symmetry here, I can actually do it the other way around. And this ability to inverse the probability or invert the probability is Bayes' theorem. That's what Bayes discovered he could do based on conditional and joint probabilities. All you have to have are base rate probabilities that are not 0. As much as you might like to have base rate probabilities that are 0, as long as they're not 0, you can do this little twist. So that's all well and good for observable characteristics like cancer and smoking, but we want to kind of scale this up, if you will, to statistics generally, not just to these kinds of events. So then what is the role for Bayes' theorem with regard to general statistical inference? Well, we're going to do pretty much the same thing, only instead of smoking and cancer, we're going to talk about values y and parameters theta. Yes, sir.
Just to clarify, the previous formula manipulations, it's applicable to frequency, statistics,
yes.
And so there's nothing Bayesian.
Other than Bayes discovered it.
But it's general.
It's quite general.
It's general
Mm-hmm. Quite general. Mm-hmm. Yep. Now it's going to be quite Bayesian in a moment, but this is basically it. That's a good point, though. So we're going to have a random variable that takes on some value once that random variable is observed. So, for example, if I'm interested in a person's socioeconomic status, that is considered a random variable. There's a potentially large number of values that can take. I don't know what they are until you tell me what your socioeconomic status is. Then, in some sense, the random variable spinner stops, and I get a value. So that's what a random variable is. Now, once you've identified your socioeconomic status, I realize that value is y, but what I'm interested in is the process that generated the observable socioeconomic status, which I have to do by providing a model for that random variable. And so we would just and that's a model. So that's right off the bat one way in which statistical theory, frequentist or otherwise, can be wrong, in that your model for the random variable might not be right. But let's assume it is. So we need a model, probability model, to explain how we obtain the actual data. Why do we need a probability model? Because that's actually unknown. I don't know what that is. And so probability becomes the language in which we are going to describe those things that we don't know, our uncertainty. So we already do this in classical statistics. In conventional statistics, we're uncertain about what that is, so we attempt to model it. Now, we typically model it as a function of a parameter. And that could be the mean, or the variance, or a regression coefficient, or a factor loading. You just think of your favorite parameter as we're going through here, because it holds for all of these. And now what we're doing is we're concerned with the probability of observing that value of that variable, given the unknown parameters theta, and we're going to write that as P of y given theta. And that is classical statistics in a nutshell. All of statistics is basically P of y given theta, and not much more than that. And what is the goal of statistical inference? Again, frequentist or otherwise, it's to estimate the unknown parameters. So that leads us then to paradigm difference number 2, which is what are parameters. So the key difference between Bayesian inference and frequentist inference concerns what we think these are. In the frequentist tradition, the assumption is that theta is unknown, right? We know that we learn that in statistics. The parameter is unknown. But that the estimation of this parameter does not incorporate uncertainty. So you might stop and you might say, well, that's not true. Don't we get the standard error of the parameter? Isn't that a measure of its uncertainty? Not in the way we're using it. It is using the term uncertainty. It is the uncertainty that arises if you could have done the experiment over and over and over again, calculated theta each time. Theta bounces around a little bit. That's the standard error. That's sampling uncertainty. That doesn't represent epistemic uncertainty about theta, what you think you might know, which is that betting idea again. So in the frequentist tradition, the assumption is that theta is unknown, but that the estimation of the parameter does not incorporate uncertainty. But in Bayesian statistics, theta is also unknown, but just like the random variable y, if we don't know what it is, we have to describe it by a language for uncertainty, and that language is probability. So what we're going to do is we're also going to consider theta as unknown and a random variable. Random variables then possess probability distributions, but in this case, it's a distribution that reflects our epistemic uncertainty about what theta might be. Now, because both the observed data and the parameters are assumed to be random variables, we can model the joint probability pretty much exactly the same way we did with cancer and smoking. In other words, here we are again. Instead of cancer and smoking, we have theta and y. So it's much, much more general. So P of theta and y is P of y given theta times P of theta. This is going to basically tell us that we cannot have a probability of 0 on theta or a probability of 1 on theta. If your probability of theta is 0, that means no amount of evidence will ever change your mind. And if your probability is 1, no amount of evidence will ever change your mind. It would be like saying the probability that, let's see if I can come up with this example because I just thought about this the other day. The probability that, I think we talked about, the probability that Hillary will win is 1.0, and if you actually held that as a prior, then it doesn't matter that Trump won, Hillary still won, right? That would be basically a probability of 1, and so you can't have bounds of 1 and 0 on these probabilities. But anyway, I digress. So we can now do the same trick with theta and y as we did with cancer and smoking. We can get this bit here, which is now referred to as the posterior distribution of the parameters theta given y, which is equal to probability of y given theta times this prior on theta divided by this probability distribution for the data non-dependent on the prior, on the parameter theta. So it's there to make this a nice probability distribution, which we can then write proportionally by just ignoring that. But there's Bayes' theorem. What now makes this Bayes' theorem, or Bayesian, what now makes this Bayesian statistics, I should say, because that's a good distinction, is how we treat the probability distribution on theta, right? Where do we get that from? Although you could argue that there's prior information here, right? Where am I going to get this proportion of individuals who have cancer in the population? Because as you can imagine, I can get there's multiple ways I can get that information. Health surveys, I can stand on the street and sort of ask people. There's all sorts of different, I can make it up. As long as it's not 0 or 1, the theorem still works. Okay. Right, so there's Bayes' theorem now expressed in terms of theta and y, representing then the relationship between the model and the parameters, some prior distribution that one has regarding one's epistemic uncertainty about the model parameters, leading to a posterior distribution. This is the learning from data quote that we had at the very beginning of the talk. I come in with some prior information regarding some parameter or parameters or parameter I'm interested in, described by a probability distribution that reflects my subjective belief about what the value of that parameter should be, and a precision around that value. I then confront my prior belief by a model for the data generated by those parameters to provide an updated estimate of those parameters given the data, which I presumably have learned something from. So equation 7 represents the core of Bayesian stat. It basically says that our uncertainty regarding the parameters of our model, which is expressed by this prior distribution, is then weighted by the actual data or model for the data, yielding an updated estimate of our uncertainty as expressed in this posterior distribution P of theta given y. So clearly, where things get interesting, where things become Bayesian, is with respect to P of theta. The prior distribution is where now things are Bayesian. So we have to talk about priors, and in the time given, I'm just going to outline these very, very generally. In Bayesian statistics, prior distributions have to be specified for all model parameters. So if you're running a regression model, all of the regression coefficients and the intercept have to have priors associated with it, and the variance of the residuals have to have priors associated with it. All parameters, and this is for all models. Now, the priors don't have to be the same. In some cases, you might have a great deal of knowledge about some relationships among variables. In other cases, you may not. There's different kinds of priors that we can assign to them. There are generally, in fact, 3 classes of prior distributions, roughly speaking. The first class of prior distributions we would call non-informative priors, which is sort of an unfortunate term, because almost any prior you place on a model parameter is going to tell me something. So it's not non-informative, it's informative. But what happens with non-informative priors is we use these to quantify our actual or our feigned ignorance about a relationship. So the example that I like to give is the example of looking at something like socioeconomic status and educational attainment. This is perfect. You planned this, didn't you? So I have like some sort of measure of achievement, and I'm just going to have this regression on SES. And I'm going to leave that alone for a moment. A non-informative prior would say, I don't know what this relationship is. Despite the fact there's 80 years of research on this, I'm going to pretend like I don't know. Right? Now, when you do frequentist statistics, by the way, the frequentist regression, it's like doing this regression for the very first time. Every single time you do it. Every single time you do it, nothing about what was ever learned about this relationship is directly incorporated into your bet about what that relationship actually should be. Now, there may be situations in which you really are unaware of what a relationship would be. Let's say a brand new study of some sort, looking at one variable versus another, and it's never been done ever before. Okay? Yes, in situations like that, you may wish to apply a prior distribution that basically specifies our ignorance about what that relationship would be. And the most direct of those is something called the uniform distribution, the most extreme, going from minus infinity to plus infinity. That's an actual distribution, probability distribution. And it basically says, I don't know what this value is. It can take on a value from minus infinity to plus infinity, and every value in between is equally likely to occur. That pretty much tells me you don't know what the relationship should be. But there are situations in which you might say, look, maybe I'm in a policy situation in which I shouldn't even provide my own prior distribution, but let's pretend as though we don't know what the relationship should be and let the data speak for itself. Another class of priors are the weakly informative priors. Weakly informative, and by the way, there are many of these different kinds, so I'm just not going through all of them. There's many, many different kinds. In the weakly informative case, we are going to put some bounds on those parameters, but we're going to let the data do most of the talking after that. So for example, I might say the relationship between socioeconomic status and educational achievement is not negative. It's never been negative. It never will be negative. It's either going to be 0 or it's going to be positive. After that, I'm not going to say anything, right? But I'm not going to let it be negative. That would be considered a weakly informative prior. It's bounding what we would consider to be virtually impossible to occur. Or in the case of variances, we wouldn't let variances become negative. So we can bound our prior distributions on variances and then let the data do the rest of the talking. And then finally, there's informative priors. An informative prior would say, well, not only do we know that this relationship has been positive for the last 80 years of studying this relationship, but it's probably somewhere between 0.2 and 0.7, canvassing the literature. So now I'm going to put an informative prior. I'm going to center my prior distribution on 0.5 with a precision that doesn't let it go below 0.2 or above 0.7. Now we get into subjective Bayesian inference with informative priors because you might disagree. In fact, we may all disagree, and some of them would say, well, let's just see what happens if we test it against this, and let's see how the results change as we test against different priors, what we call sensitivity analysis. And so here is where we get into the problem of eliciting, actually it's true for all these, the problem of eliciting prior information from a researcher. Where is this bet coming from? What literature did you look at that I did not look at that leads you to one subjective prior versus mine being another, right? All of which can be tested against the same data. So how do we do it? Well, and again, this is a whirlwind discussion, but basically, and I'll talk about this after in the second part of this today. Well, what has happened in the social and behavioral sciences has been a rediscovery of these algorithms that are now allow us to use Bayesian inference more regularly. It was impossible to analytically derive measures of this posterior distribution, particularly for complex models with many parameters, but even for simple models, this thing here is the product of your distribution of the data given parameters and another distribution. You're literally multiplying distributions together. These distributions have very nasty formulas. And now you're multiplying them together, and you have an even nastier formula when you're finished. So to sit down and say, I'm going to try to calculate the mean and the variance of this very complicated distribution, is just not worth the time. And in many respects, it's impossible to do. So rather than doing that, what was discovered was all you really need to do is program this multiplication. In other words, program the expression. Now, once you can program the expression, then what you can do is simulate from that distribution using simulation methods in computer algorithms. So now what you're going to do is you're going to simulate from this complex distribution instead of having to solve for it. And you're going to take thousands and thousands and thousands of simulated parameter values. And what you're going to get when you're finished is the actual posterior distribution of the parameters. Now, once you have this posterior distribution of the parameters, then you can summarize them the way you would summarize any distribution. Calculate the mean, calculate the standard deviation using just traditional software packages. But now what you're doing is you're doing this on the posterior distribution. So this is what's called Monte Carlo integration. And a particular type of Monte Carlo integration is called the Markov chain Monte Carlo integration, or MCMC, which I'll talk about much more in the second half of this. Two popular methods for this are the Gibbs sampler and the Metropolis-Hastings algorithm, but there are many others that are showing up now in other software programs. Okay, so more about computation when we get to the tutorial part. The next thing we want to do is do hypothesis testing. And as you know, the conventional approach is approach based on Neyman and Pearson. And the problem with this approach, as you probably know now because the literature is so filled with these debates, is that it turns out to be very difficult for pretty much everybody to understand or to really get right. And I want to spend just a little bit of time on this, if you don't mind, because this is where people are starting to get attracted to Bayes, because it's supposedly an alternative to classical hypothesis testing. And I want to talk about that for a moment. Fisher had two approaches to hypothesis testing, a kind of early approach and a later approach. The basic idea was that you had a chosen significance level. For Fisher, it was 5%, but he never said that that had to be it for all time. Once a test is conducted, the result was either significant or non-significant. And if the result is significant, then the hypothesis is rejected. If it's not, then no conclusion could be drawn. So Fisher, perhaps correctly, had it right by saying that by arguing that his approach was based on looking at how data could inform the evidence for a hypothesis. But then Neyman and Pearson came around a little bit later, and divided up the world into a decision problem, requiring two hypotheses to be specified, the null and alternative. And then the idea was to create an experimental design designed to be able to test or to take one of two specific kinds of actions. So it was about making a choice. It was not about evidence against the hypothesis. Now, if you're going to make the choice between one hypothesis and another, then there's two kinds of errors you can make, a type 1 and a type 2 error. So the goal was not to assess evidence, but rather to have a setup that allowed you to make take a decision that had a low probability of being the wrong decision. It's basically the idea. Any kind of prior belief about truth was irrelevant in the Neyman-Pearson context because it wasn't about scientific truth. It was about decision making and trying not to make the wrong decision. Right? Why did these two areas get completely conflated? It had to do with the p-value. So in Fisher's world, the p-value was a matter of convention, 0.05. And then the result was the outcome of the data. But in Neyman and Pearson, the p-value, though coming out after data was collected, the type 1 and type 2 error probabilities are determined before the data are collected, not after. And in fact, in the Neyman and Pearson approach, the problem is one of finding a balance between type 1 error, power, and sample size. This is an experimental evidence. So a Neyman and Pearson approach was best suited, and is best suited, for experimental planning. The problem is that it has always been followed up by Fisherian logic. You start with some Neyman-Pearson idea in your head, and then you actually move to Fisher when you're finished. This balance between alpha and the p-value is always ignored, and the point is that the p-value and alpha are not the same thing. And as you probably are well aware, this issue of confusing alpha that is presumably set up ahead of time with the p-value, which is a function of the data, is made worse by the fact that software packages give you the option. 0.01, 0.01, 0.05, star, 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 right? So this can lead you to set alpha ahead of time, as per Neyman and Pearson, which would be a good thing to do, and then communicate a different level of significance after you've collected the data. Now, this conventional practice is worse than I'm describing because what we see in the literature now are these nonsensical phrases such as a result is trending towards significance. And I went to this talk a few weeks ago where somebody had presented not just that one, but about 30 other versions of this. Trending towards significance, balancing ever so slightly towards significance, just over significance, running away from significance. I mean, there was like 30 of them that they had found in the literature. So this is I'm not making this up. They had found this stuff in the literature. So the problem seems to lie in the p-value. And so the question is, what is the p-value? The p-value is a type of an argumentation. It's called reductio ad absurdum. And this is Fisher's definition, not my definition. It's a type of argumentation that attempts to establish an assertion by deriving an absurdity from its denial. Therefore, you can argue that the assertion must be accepted because its rejection would not be defensible. So the p-value is thus properly interpreted as the probability of observing data at least as extreme as the data that was actually observed, computed under the assumption that the null hypothesis is true. So the p-value is based on data that was never actually observed. That's the first weird thing about it. You guys remember calculate a statistic, then you go to the back of the book to find out what that is. You know what that thing is in the back of the book? That's the asymptotic distribution of the test statistic. And what you're doing is you want to see whether or not your p-value, your test statistic, is greater than something that was never actually observed in the data, nor could it even possibly have been observed in the data. So the p-value is obtained by referencing the value of an observed-to-test statistic based on the study at hand to hypothetically replicated data under the assumption that the null hypothesis is true. Second part of this, the null hypothesis is never true in reality, and it's typically not even what we're interested in. Typically interested in the nil hypothesis that we wish to reject. So it is important to emphasize that there's nothing within the hypothesis testing paradigm that requires the null hypothesis of no effect. And in fact, any theoretically justifiable hypothesis can serve as the null. So to summarize this, the p-value does not quantify evidence for a hypothesis. Rather, it provides a measure of the probability of an outcome not actually observed, computed under the assumption of a null hypothesis that will not likely ever be true in any population. And moreover, is typically not what we're even interested in. And so to quote an early criticism of this by Jeffries, sarcastically he said, "This seems like a remarkable procedure." So from the Bayesian point of view, how do we now do hypothesis testing? Well, the beauty of the Bayesian approach is that we have the posterior distribution to work from. So if in fact, once we're finished with this MC-MC analysis and we're getting the actual empirical posterior distribution, the first thing we can do is summarize this. We can get the mean, we can get the median, we can get the mode, we can get the standard deviation, we can get the intervals, which I'll talk about in a moment. We can do everything about this. The beauty of the full posterior distribution from a Bayesian point of view is we can answer questions that you can't answer as a frequentist, whether you think so or not. For example, I can ask the question, suppose 0 is over here. What is the probability that my effect is greater than 0? And then I just answer it. Points up. You can't do that as a frequentist. You can answer that question. You can say, what's the probability that my effect is between here and here? Just, what is it? In other words, I have the full posterior distribution to work with. It's not significant, non-significant. I can work with any question I wish to ask that's of policy relevance or clinical relevance off of this posterior distribution in an extremely intuitive way by just reading off the probability distribution. So summarizing the posterior distribution is what we're interested in. As I said, we can get the mean, the mode, and we can get intervals. The intervals are very important. Recall that from a frequentist point of view, a confidence interval requires that you imagine an infinite number of repeated samples and that it's the confidence interval that's bouncing around, right? So that the correct frequentist interpretation of the confidence interval is that 100 times 1 minus alpha percent of the confidence interval formed a particular way will capture the 2-parameter mu under the null hypothesis, meaning the null hypothesis is assumed to be true. So that the probability that the parameter is in the interval or not is either 1 or 0. It's a coverage under a frequentist idea of coverage, basically. The credible interval, by contrast, the Bayesian interval, called a credible interval or a posterior probability interval, is different. Once I've sampled from the posterior distribution, I can then form any interval I wish, any interval of substantive importance to you, including, if I want, the 95% interval. Now, what does this mean? It means that the probability that the parameters in this interval is 0.95. It's that simple. It's that intuitive. Now, of course, the posterior interval can include 0. 0 could be here. What's beautiful about this is that you can ask the question, yes, 0 is here, but it's over here. What's the probability that most of the mass lies above 0? I can ask that question. Right? I can change these intervals to anything I want that's, as I said, of relevance. But if 0 is in this interval, all that means is 0 is a credible true value of the parameter. 0 could be the true value. And notice, what is important to notice here is that this idea is entirely different from the frequentist interpretation of the confidence interval. And in fact, one can argue that it makes more intuitive sense, and arguably what it is you actually want to know the answer to. So continuing with model building, and I'm about to wrap it up, I think. I might skip Bayes factors, just in the interest of time. The goals of model building and frequentist and Bayesian analyses are basically the same. You're going to specify some kind of model you're interested in. It's a regression model or a structural equation model or something like that. You're going to you're going to estimate the parameters, fit the model to the data, obtain from a relevant population. You're going to evaluate the model and possibly modify the model. And then you will have done this many, many times. Eventually you stop and you choose a particular model, and you use that as the one that you're going to do your analyses and discussions of. But there are important differences. For one thing, at the Bayesian stage, we have a probability model not only of the data expressed in terms of model parameters, but a probability model for the parameters themselves. So now there's a greater sensitivity to misspecification in the Bayesian framework because there's lots of different places this can go wrong. So Bayesian statistics is not a free lunch. It's not going to give you it's not going to be easier to find well-fitting models. If anything, it's actually going to be harder because there's more you have to think about. So if a model fits the data, or maybe if the model doesn't fit the data, it implies that the full probability model fits, and their lack of fit may be due to incorrect specification of the model itself. You just got the model wrong. The prior distributions may be wrong, or both. Another difference has to do between the Bayesian and frequentist goals have to do with the justification for choosing a particular model among a set of competing models. Typically, in the conventional domain, we choose a model that best fits the data. And so we run around trying to find models, we modify models, we add variables, we take variables out, and ultimately we choose one and say that model fit the data best in some sense. And that's certainly the motivation for model building and model choice in SEM, at least conventional SEM. But in the Bayesian domain, the choice among competing models is based on which provides the best posterior predictions. In other words, the focus of attention, by and large in Bayes, is the predictive quality of the model, not fit in an up and down sense of the word. That is, the choice among a set of competing models should be based on which model will best predict what actually happened. Now, in the model choice literature, in the Bayesian model choice literature, if you're going to choose a model among a set of models, a very intuitive approach is based on something called the Bayes factor. The Bayes factor provides a way to quantify the odds that the data favor one hypothesis over another. Notice how I wrote that, because if you look at the formulas, which I'm not providing in this talk, you would see it, that it's odds. So it sounds like betting again. I have two models, the same data. What are the odds that the model prefers, the data prefer your model versus mine? And notice the way that I said it. It's the question of whether the data prefer your model over my model, right? So we're competing models on the same set of data and looking at the one and only one data set that we have in order to make the judgment as to whether or not the data prefer my model over your model. There's no notion of this frequency idea of conducting the same study over and over and over again. And the Bayes factor gives rise to the Bayesian information criteria, which is used in a similar context. Now, the problem with model choice is that there's an inherent uncertainty in that choice. If I have a variety of models to choose from, that is to say there's a space of models, maybe the true model is in there, maybe it's not. The fact of the matter is I'm not taking into account the uncertainty in that choice process or the uncertainty across the model space in order to, in fact, choose a model. So there's a very nice quote. Standard statistical practice ignores model uncertainty, not parameter uncertainty, model uncertainty. Data analysts typically select a model from some class of models and then proceed as if the selected model had generated the data. This approach ignores uncertainty in model selection, leading to overconfident inferences and decisions that are more risky than one thinks they are. So the way to deal with the model choice problem is not to choose. In other words, instead of choosing a single model, why not average over the space of possible models that one can consider, right? But not just a simple average of the parameters of different models, a weighted average, weighted by the quality of the model. So this approach is referred to as Bayesian model averaging. It's an area that I'm working in right now. The basic idea is that each model has a measure of model uncertainty. Rather than choosing a particular model, which may have a high degree of uncertainty to it, we're going to average over a large set of models, weighted by each model's measure of its uncertainty characteristics. The result of doing something like that is related to the problem of prediction, which we can show. Namely, if I obtain an average of models, I will get better prediction than any single submodel I could have chosen among the class. Always, I will get better prediction in a particular sense. You probably have heard of these things, polls of polls. Is that familiar to some of you in here, where you're taking the average of different political polls, but then you're weighting them by the quality of those polls? That's Bayesian model averaging. What's happening is, although it's being updated quite a bit, what's happening is that you have this past performance of these political polls. Some polls are better than others. All of them have some degree of uncertainty. Even ones that are really good are not perfect. And now what you're going to do is you're going to say, the best poll I can get is the one that averages across all of these polls, but not from a simple average, taking into account its previous measures of quality. Weather forecasting works very much the same way, by the way. These forecasts are based on models that are continually being updated and being basically averaged by their very recent past performance in terms of getting the weather report correct. So let me then, this was very quick, let me summarize then the Bayesian advantage, and then maybe there's some time for questions. The major advantages of Bayesian statistics over frequentist statistics are many. The first is coherence. Now, coherence is a particular topic. It's not a simple thing. It sounds like it's just like this is coherent and the other is incoherent. That's not the case. Coherence refers to the fact that if you are required, as you are being a Bayesian, if you're required to state your subjective probabilities about certain events, those subjective probabilities have to be aligned with the theory of probability, with the axioms of probability. Otherwise, your bets, if you will, are incoherent. So what that means is I can create a kind of a bet with you in which, if you're not paying attention to the laws of probability, I can make sure that you lose money regardless of the outcome of the bet. It's a typical kind of a book, they call it. They call it a Dutch book. And a Dutch book, which sounds mildly offensive, but the Dutch book is a type of a bet in which you lose no matter what the outcome is. Why? Because you're not playing according to the laws of probability. But Bayes forces you to speak in probabilistic terms so that you know whether or not you're following the laws of probability immediately. Whereas in the frequentist case, those are all hidden in the background. Your behavior could be quite incoherent, and you would never know. The Bayesian advantage is its flexibility in handling very complex models through MCMC, but that's got to be treated with caution. Basically, what we're saying here is you might have a situation in which your statistical model is so complex that it can't be analyzed in the usual frequentist way. Well, that's okay. As long as you can program it into a computer, you can use MCMC, right? So now what you're using is an algorithm to do the computations. But these algorithms require you to have priors. So if you're using MCMC simply because you do not want to take the time to figure out how to solve this from a frequentist point of view, don't think you're not being a Bayesian. You are, because it's going to put priors on these computations anyway, and they're going to could have a major influence on your results. Number 3, the inferences are based on the data that are actually observed. There's no notion of repeated sampling or data that are not observed. So the idea here is you have one and only one data set in your hands. That's the one you've collected. And the question is simply, is there evidence in this data set for a hypothesis I'm interested in? It is all about quantifying evidence. So these are actually somewhat related. It's about quantifying evidence in the form of odds. So it has that betting sound to it again. Number 5, I just added this actually last night because it occurred to me. Intuitive probability statements. And that's what I mean by reading things right off of here. You can make probability statements about any question that you're interested in from the posterior distribution in very intuitive, very, very straightforward ways. And then it's the only way I know to incorporate prior knowledge. You know this to be true. You write these big papers. These papers have big introductions with big literature reviews. Then you get to the point where you do your analysis, and nothing about the literature review was ever used in the subsequent analysis in a direct way. There's no priors in the frequentist point of view. So to wrap this up, the Bayesian school of statistics, you'll probably be surprised to hear me say this, is arguably superior to the frequentist school as a means of creating and updating new knowledge in the social sciences. The Bayesian school of statistical inference is the only coherent approach to incorporating prior information, leading to updated inferences and growth in knowledge. It represents an internally consistent and rigorous way out of the p-value problem. And it approaches model building, evaluation, and model choice from a predictive point of view. And so, of course, the full benefit of the Bayesian approach to research in the social sciences, to the work that's done here in GESIS, will be realized when it's more widely adopted, and in particular, as we examine whether it yields reliable predictions that actually advance knowledge. Thank you. That may have been the fastest I've ever gone. That's a land speed record. Do we have any time or no time? I wasn't paying attention.
We do have
actually.
a little bit of time for questions, so please go ahead.
Yes, ma'am.
Thank you for this presentation on YouTube Bayesian.
Mm-hmm.
Very helpful. I'm wondering, if I run a model with an informative prior,
Mm-hmm.
and then conduct sensitivity analysis
Mm-hmm.
using a non-informative prior,
Yeah.
it's on subject. What do I know then, and what do I do? Because does that tell me which model is better? And maybe just, couldn't it be that my informative prior is just wrong?
Yes, it could be. So there's lots of ways I can answer that question. The first is that you would always want to do a sensitivity analysis. The second is one thing I did not bring up here because it really is too involved, is that the other thing that Bayes can get you out of in a way is the sample size problem. But that's not, again, a free lunch. And what I mean by that is that in very, very large samples, okay, the results of a frequentist analysis and Bayesian analysis will be the same. This we know, and that's a good thing when you start to think about it philosophically. It's exactly the way it should be. And what that also means in contrast is in very small sample sizes, the results can diverge tremendously, okay? And so the fact that you're finding a difference between the results of a non-informative prior versus an informative prior could be that the sample size, in fact, is now small and that the priors are starting to matter tremendously. So the first thing, of course, would be to examine that sensitivity, as you said. And then the second thing would be to look at other measures of model choice, such as the Bayes factor, comparing the model with informative priors to a model with non-informative priors. One of them will be better. In terms of priors that could be very, very wrong, in small sample sizes, you're likely to see that. Just in the results, they're not going to make sense. They won't make sense. And if they're really wrong, it's possible that a model with non-informative priors would actually fit better than a model with informative priors that just happen to be really off base. So you would have multiple ways of diagnosing that. All of this, by the way, assumes that the MCMC algorithm has converged nicely and that everything is okay. But you get into the sample size trade-off, as you do with frequentist statistics, but for different reasons. You get into a sample size trade-off between the sample size and the priors and the precision of the priors. So, yeah. Does that help? Okay. Yeah.
Yeah, thanks very much for the presentation.
Sure.
A follow-up comment on Karina's question. I mean, this is another advantage, right? That if you don't have enough data, for instance, I'm coming from field of meta-analysis, where we don't have enough data, so you could help the estimation process by specifying one prior or multiple priors in terms of a sensitivity analysis, and then you could actually do your calculation, your estimation, right? Which would not be possible if you would run the frequentist approach.
That's correct.
So
you also run into type 1 error problems in a frequentist approach. It wouldn't run into here. It's not doing the same thing. So yeah, there's no reason why you can't do it. You're getting predictive validity information from the Bayesian approach as well. I should say one thing about meta-analyses. Those are perfect places to get your priors, right? So if you have like 60 studies and you're about to do the 61st study and you're wondering where your priors ought to come from, well, how about from the meta-analysis that was done on the 60 ones that are prior to that? Yeah, so that's correct.
One thing that I was always wondering, I'm a sociologist by training. One thing, and you mentioned, for instance, in point 5, that one advantage is that you get a better interpretation of your p-values and your confidence intervals in terms of credibility intervals. I was always wondering why not more people use these methods in our typical sociology journals.
Bayesian statistics?
Bayesian statistics, yeah.
Oh.
I mean, I used it, for instance, in my PhD thesis. I, of course, was able to tell my advisor, okay, the probability that this estimate lies between whatever it is, like 95%. So, and I tried once to publish a paper using these methods, and it got rejected.
Well, we got into this conversation the other day, in fact, and I think that the reason for that is that there's a tendency in sociology, but also in psych and education and all these other fields, to dichotomize evidence. What people want is they want to know, is the intervention or the treatment or the effect up or down? And that evidence is not dichotomous. Evidence is continuous, is the argument. And this, what the probability model of Bayes gives you is a continuity of evidence up to a degree that you're interested in for sociological purposes. To dichotomize evidence is one of the worst things that one can possibly do, but that's what we've gotten. So the pushback that you get is usually because somebody wants an up-down answer. The irony of that is 0.05 is entirely arbitrary. So it's silly. It's a silly sort of problem we've gotten ourselves into. I think it's changing, but quite slowly. Yeah.
I was also thinking about the priors that you put into the that you include as assumptions, and given the replicability debate we have at the moment, if you talk about that there are 60 prior studies, and in a meta-analysis they show that we have an effect of d equals 0.2 or so. Our recent results show that we cannot really trust findings that will all go in the same direction. This is more a hypothesis confirming testing. At least in some areas. So, what effect might this have on the analysis that you do?
I don't know. So this is, what do they call that? I can't remember the name of hypothesizing after the facts are known or something like that. But the issue of the replicability crisis has crossed my mind, although I've never contributed anything to that literature, because I keep wondering what it is it's not actually replicating. And I think it's the significance test. So some studies are statistically significant, some studies are not statistically significant, and people get panicky about the fact that the significance isn't replicating, right? And I kind of always wondered, well, if you're a frequentist and you actually did the study over and over again 1 million times, it wouldn't replicate.
I think the second part of the story is that you only publish the significant
the file
studies,
drawer.
so you have the positivity bias.
Yes.
Here.
So in the case of Bayes, you wouldn't be forced to have to do that, because you're simply stating the credible intervals of your effects. And 0 might be a credible interval for some parameters and not for other parameters. So you're really just stating things in terms of probabilistic terms. But the file drawer problem is due to the fact that we have this dichotomization of evidence. So it seems to me that what has to change is the idea that the evidence doesn't have to be a dichotomy, that there's evidence for or against, but rather a range that evidence can take on, and that it has to do with a substantive problem to generate whether or not a particular credible interval has a range that's of substantive importance. So if I have a credible interval that goes from, say, let's say there's some number here, take out the 0, whatever, so, x, some number x and some number y, and that the true value has a 95% probability of being between x and y. X and y also take on some meaning. So the true value can be here with a 95% probability, but x means something, y means something. And so the nature of the conversation about what constitutes an effect is no longer there is one or there isn't one, but rather here's the range of values this effect can take on, with the true value having a 95% probability of being in there. So I think that where it's going to take some time for Bayes to kind of leak into the way in which we do these things is going to be because how we express what we know is going to have to be different, I think. It just has to change.
Just quickly follow up on this. If I understood you correctly, you said before that there is this epistemological uncertainty.
Right.
Maybe there is no true value. Now you say it can be anything between x and y, and that's all we can say. Is it true or not?
No, I mean, basically from a Bayesian point of view, you are saying that there's a 95% probability that the true value is between those.
But it can be, theoretically, it means it can be anything.
It can be anything in between.
Like in quantum mechanics.
Right, it can be anything
what
in
we'll
there.
observe, right, it can be anything. And
right, for continuous
true,
distribution,
right?
that's
Not
right.
one true value.
That's right, there's not one true value, but yeah, you're right. I mean, that's sort of tricky. We are making an assumption that there is a true value in there.
In Bayesian still
yeah.
Bayesian.
Oh yeah, yeah, sure.
Really?
Yeah.
But then
but we're just describing we're describing because it's not an issue of describing that saying that the true value is probable. What we're saying is that our knowledge of that true value is described by probability. It's epistemological. That's right. Yeah. This is an epistemological uncertainty. And so the way in which we discuss what it means to say that we have found something, or that we think that the effect is in this range, is different than simply saying it is statistically significant or not. Right? That's why what's taking so much time, I think, is partly being able to find this language that's different from the language that we've typically been using, though there's a strong pushback to use that kind of language. Even M+ does this now, I think, where in its Bayesian things, it has like little stars next to it. I mean, it's like they can't escape it for some reason, which I don't really quite understand. But, I mean, whatever. Yeah.
But maybe the right approach is to say there is no true value in the nature, right? And then that's what quantum physics now say about the natural world and social world. Most of it seems to me. You cannot predict essentially, right? But maybe you can say the interval, but you cannot predict.
The setup of the theorem and the setup of the statistical models suggests that there's a true value you're after. You're just uncertain about what it is. And that's all you're saying is that the true value has a 95% probability of being in here. But obviously, there's an infinite number of values between here and here. So we don't, at some level, you're right. We don't know what it actually is. But we certainly can describe the bounds around it, which is pretty much all we can do in our precision around those values. Yeah. Anything else? Yeah.
Yep. Oh. Right. Just out of curiosity, where you would place a maximum likelihood estimation compared to the two camps, frequentist or Bayesian?
Well, there's a difference between maximum likelihood estimation and likelihood. All right. Yeah. So this thing, let me fly back. I know you know this, but I just want to fly back to here. This thing here, that little bit right there, or if it's easier, just look at this. This py given theta, that's the likelihood.
Yes.
Not maximum likelihood. That's the likelihood. And so clearly, Bayesian statistics has a component having to do with likelihood theory. It just adds this thing about model parameters, prior distributions. That's it. And the other thing I wanted to mention before I get right to your answer is that this thing here can be written as the likelihood, L of theta given y, the likelihood of theta given y. And you're back to normal likelihood theory. Now, the maximum likelihood estimator is in infinitely large samples is the mode of the posterior distribution. So what is this? Anyway, so the let me go back over here, if you don't mind me for a moment. Excuse me. Oh, I guess I passed it. Well, here it is. So I can, once I get this posterior distribution, I can calculate the mean and the variance and the mode, the MAP, the modal a posteriori value of the posterior distribution is the maximum likelihood estimate when the sample size is infinitely large. They converge. So that's where ML comes in. You won't see very much difference between the, you won't see any difference really for very large sample sizes. The problem is, and what you might be thinking is, okay, how large is large? And the answer is you do not know, because I've done this kind of analysis with PISA data both ways just for the fun of it. And I'll look at like the US sample of PISA and not do anything fancy with weights, just like the US sample of PISA, 5,000 US kids, and I get differences between the Bayesian result with non-informative priors and maximum likelihood estimation. Big differences, not really big differences, but big enough to realize that 5,000 is not large enough of a sample size, even though most people would think that's a pretty big sample size. So you don't know, and then once you start putting informative priors on this distribution. So this is true. The modal a posteriori convergence to the maximum likelihood estimate is true for uniform priors or conjugate priors, conjugate normal priors. But if you have your priors way, way, way off, then you're going to need that much more of a sample size to. Yeah.
Okay, if I may interrupt the discussion here.